Yeah. So I'm finally a PhD student at IISER Bhopal, India, and I work on formation of quark stars from the neutron star. And neutron neutron stars are neutron stars are formed from cloud of gas when they undergo main sequence. They become main sequence star, then they undergo the red giant phase, and neutron stars are formed. The neutron stars which are formed at the end of a star's life, will they remain neutron star, or will something happen to them in their lifetime that they get converted to quark star? Is this question I have addressed in my research, and I'll be presenting that. The motivation for this comes from the dense cores which are present inside the neutron star. The neutron star structure can be obtained by solving the TOV equations. The TOV equations are hydrostatic equilibrium equations, same as that of Newtonian gravity, with some terms which are special relativistic and GR correction. This is the mass sequence for a neutron star. Y-axis is the mass, x-axis is the central density. Here we can see that a 2 solar mass neutron star has central density of 5 into 10 power 14 gram per centimeter cube for this given chosen equation of state. The dense matter properties are not clear, so we have to choose different equation of states which exist. And for this particular equation of state, we can see a 2 solar mass has a central density of 5 into 10 power 14. A 2.5 solar mass neutron star has a central density of 1 into 10 power 15 gram per centimeter cube. And the neutron star mass versus radius is shown in this particular figure. And we can see that a 2 solar mass neutron star has a radius of about 14 to 15 kilometers. So a 2 solar mass size thing is contained in just 15 kilometers. The neutron stars are quite dense and the densities are quite high. The average nuclear saturation density that we see in the periodic table elements nuclei is 2.3 into 10 power 14, and the neutron star densities are much higher than that. And this says that the neutron star cores are much dense. And there is a QCD conjecture which says that a density is about 3 to 10 times the nuclear saturation density. The nuclear matter is no longer the stable ground state. The three-flavor quark matter consisting of up, down, and strange quarks is likely to be the ground state of high-density matter. This was suggested by Witten in his seminal work in 1984. And according to it, the dense cores which are present inside the neutron star, there is probability that the nuclear matter is not stable and it should get converted to three-flavor quark matter in which up, down, and strange quark is present. And this is the QCD phase diagram, and the neutron star densities overlap between that of the nuclear matter and also of that of the quark matter. And there is a particular way in which the neutron star gets converted to a quark star, and this is a two-step phase transition process. According to the two-step phase transition process, the neutron star consists of neutron, proton, and other particles, and inside them the quarks are present. Due to the deconfinement process, the up and down quarks which are present inside the neutron star will get deconfined, and you will have a sea of up and down quarks. This results in formation of a two-flavor star. And after this up and down quarks are formed by the deconfinement process, there will be weak decay process, and this will lead to formation of up, down, and strange quarks. And this way we will get a three-flavor star. This is also a strange star. So by a two-step phase transition process, a neutron star will ultimately become stable with quark star. And this can happen in a proton-neutron star
5 minutes.
after their core collapse supernova, or in cold neutron star during their evolution, and also in hypermassive neutron star after their birth. And sometimes the neutron stars are present in binary system, and also the neutron stars sometimes undergo spin up or spin down or glitch phenomena, due to which the central density can increase, and the increase in central density can give rise to shock waves, and the shock waves can convert the nuclear matter to quark matter by the deconfinement process. So this is the dynamical phase transition model which we have proposed. According to that, a neutron star undergoes a density fluctuation. This is the hydrostatic equilibrium configuration. This is a small density fluctuation at the center, and this density fluctuation, which results from accretion or sudden glitch phenomena, can result in a shock wave which propagates forward. And this shock wave can convert the nuclear matter to quark matter in the region surpassed by it. The shock wave will increase the density and pressure of the nuclear matter, which will result in deconfinement to the quark matter. This is our model. And we have done general relativistic hydrodynamic simulations. And you can see the discontinuity results in a shock wave which is propagating outward. And high density quark matter is formed. For combustion, we employed these equations to replace the nuclear matter with the quark matter in the region surpassed by the shock. The results reveal that the phase transition takes place in about 50 microseconds. This is a very rapid process. If a neutron star undergoes a particular shock-induced phenomena, then in about this particular time scale, it will become a two-flavor quark star. And this is similar to something that we see when a comet comes and hits our Earth, and that results in the shock wave, and shock wave completely results in combustion of the Earth matter. And this combustion happens up to the place where shock strength is high enough. And similarly, and during the phase transition process, which I told now, the star's density continuously undergoes rearrangement. And we have done the phase transition up to 5 kilometers where shock strength is high. After 5 to 6 kilometers, we only the pure shock propagates, doesn't cause any phase transition. And the gravitational wave can be extracted by this density change. And we obtain the gravitational wave. It comes out to be a burst type of signal, which is having a time scale of 10 power 5 seconds, 10 power minus 5 seconds. And the frequency comes in 10 power 5 hertz. This type of gravitational wave signal, which can originate from shock-induced phase transition, cannot be observed in LIGO-Virgo detectors, but it can be observed in the future high-frequency detectors. But is there any other way we can observe the phase transition? Because these signals are not in the range of the present detector. The answer comes from the second step of phase transition. The first step was the reconfinement. The second step, due to weak decay, up, down, and strange quarks form. This particular thing can be modeled by diffusion type of equation. And the time scale for this particular thing comes out to be in about milliseconds to second, depending upon the temperature of star. So this is shown for 10 power minus 2 MeV temperature. This is shown for 5 MeV temperature.
2
the
minutes.
Diffusion time scale of the 2-flavor to 3-flavor conversion. And during the 2-flavor to 3-flavor conversion, the star's baryonic mass remains constant because the baryons are not lost from the star. And this is the black line, which shows this is a density profile during the conversion process. This black line represents the 2-flavor star's density profile, and this particular brown line represents the density profile of the 3-flavor star. And because the baryonic mass is conserved, these two profiles have the same baryonic mass. And when a 2-flavor star becomes 3-flavor star, its density increases and its radius becomes less. So a 2-flavor star, when it becomes a 3-flavor star, it contracts and its density profile also changes. This density profile change also can produce gravitational wave. We have not performed any full hydrodynamic simulations of this. We have just carried out this metastable states in between these two configurations and obtained the gravitational wave. And the time scales comes out to be in millisecond to second.
1 minute. Please
temperature
conclude.
of star. So this is the possible gravitational wave signal which can originate and by which we can identify the phase transition. Initially, there will be neutron star which will be rotating, and from which we will have rotating gravitational waves. And then due to the phase transition, disconfinement phase transition from hadronic matter to 2-flavor quark matter, which happens in 10 power minus 5 second time scale, we will have a particular gravitational wave imprint. Then 2-flavor to 3-flavor conversion, when it will happen, so that ultimately the star becomes stable.
30 seconds.
We will have a gravitational wave signal. And finally, we will have a hybrid star or quark star which will get formed, and there will be gravitational wave emission from this. Either by change of this continuous gravitational wave signal from the neutron star to quark star, we can identify that in between this, it has underwent a phase transition, or else we have to detect this hadronic to 2-flavor conversion phase transition in high frequency detectors. And this particular gravitational wave signal needs much refinement, and this can be observed in the LIGO and Virgo detectors because this time scale is in milliseconds to seconds. Yeah, thank you.
Great, thank you very much. All right, so Behan has a question for you, Prasad. What is the minimum mass neutron star that phase transitions took place in your study?
In my study, I have taken a neutron star of 1.6 solar mass, and it depends upon the equation of state. And this study I did before, like 3 years back, and that time we didn't have this NICER data and those constraints. So as of now, I have to check which particular neutron stars will be favorable for this phase transition. Mostly it's in high massive neutron stars, which densities can be few times that of the nuclear saturation density.
Great.